They had a loop like a bangle or something which is made up of a conducting material. That particular loop, they placed it in a uniform magnetic field. Whenever there is a change in magnetic flux linked with the coil, an EMF is induced. There is no actual contact, there is no power supply, it is induced. When I try to bring this magnet close to that particular loop, what happens is that current flows in such a manner that it tries to reduce or it tries to repel away this relative motion. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we are going to start a new chapter, that is Electromagnetic Induction. The only induction you might be familiar with is the induction cooker you have at your home. So is there any relation, and what exactly is electromagnetic induction? Obviously it has something to do with electric and magnetic fields and the new concept that is induction. So without further ado, let's see what is electromagnetic induction and what this chapter holds for us. So you actually might have a doubt. That is, we learned about electric field and we learned about magnetic fields. But in all our lives, when everyone says something about electric and magnetic fields, it's always electromagnetic fields. Like they are both complementary to each other. Who found that it's complementary? Who said that they are symmetric to each other? Who found all this? And why are they like that, behaving like they are the one mirror image of the other? All these questions were actually thought by scientists before also, and actually it was Maxwell who united electromagnetism, that is electric and magnetic fields. He brought them together and unified, bringing up the electromagnetic theorems. But before that, people were discovering that magnetic and electric fields were complementary to each other. That is, we saw that when a charged particle is at rest, it produces an electric field, and that particular electric field was a resultant of the magnitude of the charge. Bigger the charge, bigger the electric field around it. That was the first few chapters we studied on electrostatics. That was static charges. And then we studied what happens when a charged particle then moved. When a charged particle entered into a dynamic state or just simply executed motion, then the charged particle which was moving created a magnetic field. So moving charges produces magnetic fields or magnetic effects. That also we studied. Now the question is, moving charges produce magnetic field and there is also an electric field innately because of the polarity of the charge. Now the question is, if a change in electric field produces a magnetic field, can the reverse also be true? That is, a change in magnetic field, can it produce electricity? That is the innate question everyone was asking. Now, people were actually discussing it and trying to find a way to prove this theorem. That is, can this be possible? Can a change in the magnetic field also induce an electric field? Or simply, can a change in magnetic field produce some effect in the electric field? So, the first person who achieved this and conducted a series of experiments were Faraday and Henry. Those are two scientists, two pioneers in the field of magnetism and electrostatics. So, they found out that these particular changes were very evident. So how they did the experiment was, it was a three-part experiment. Part one was getting the setups ready. So Henry and Faraday were doing an experiment, and the way they did that particular experiment was, they kept a solenoid like this connected to a galvanometer. Now you know a galvanometer indicates small deflections of current because you already learned that. Don't ever forget that. So there is a solenoid connected to a galvanometer. Remember, it is not connected to any source of battery. There is no current flowing through this particular solenoid. It is just a blank solenoid connected to a galvanometer. Right now, the galvanometer needle is sitting at 0, no deflection. But what Henry and Faraday did was, they brought a magnet. They brought a magnet like this near a solenoid. And they observed, is there any change? Like, will something happen? And it was found that nothing is happening. Whenever they brought a magnet near to this particular solenoid, nothing was happening. No change was produced. As everyone expected, nothing is happening, no change is happening. Now he accidentally moved, or purposefully, he moved this magnet into the solenoid. So he moved this magnet into that solenoid. And suddenly Faraday and Henry observed that the galvanometer needle suddenly just deflected. So the galvanometer needle was like this, and the moment the magnet went inside to that particular solenoid, the needle just deflected. Just once it deflected, and as soon as they stopped moving the particular magnet, that is, when the magnet was actually inside this particular solenoid, the galvanometer needle deflection stopped. So again they observed the magnet after some time also. There was no deflection, no change. So okay, they said okay, it might be some error with the equipment or something. So they tried to take the magnet back out again. And again when they were taking the magnet out, the galvanometer needle deflected. So they observed that whenever the magnet was kept or whenever the magnet was moved into the solenoid, there was a deflection in the galvanometer needle, and whenever the magnet was removed from the solenoid, there was a deflection in the galvanometer needle. So they assumed that relative motion of the magnet is causing that particular deflection. So they tried one more thing. They kept this particular magnet just like that, and they tried to move the coil. They tried to move the coil back and forth. Same thing happened. Whenever these both were at rest, no change was producing. But whenever there was a relative motion between any of these two, then immediately the galvanometer needle was deflecting. This puzzled the scientist. So what exactly is happening? There is no current running through that, and galvanometer is an apparatus that measures current output. So they assumed, okay, what might be the reason for that? They arrived at the inference that this particular magnet or this particular solenoid is causing some change. But they did not actually know what was changing. So the only assumption that was true was the only thing that is changing in this particular position is that magnetic flux. Yes. So you know that this particular magnet will have magnetic field lines around it. That is, this particular magnet will have immense amount of field lines around it. So whenever this magnet is going into the solenoid or out of the solenoid, then let's say in this particular area, the area is A, in this particular area, now the magnetic field line concentration is 0. But when I move the magnet into the solenoid, that particular area which is having 0 magnetic field concentration is now changing to a higher value, a positive value, which means we are introducing a change in magnetic flux in that particular area. Magnetic field lines are penetrating that particular area. Once it was 0 and suddenly there was a change. It increased. Then there was a deflection in the galvanometer. And when we are removing the magnet, what happens? We are decreasing the number of field lines in that particular area. So magnetic field line concentration increased and decreased. So the only thing changing there is the magnetic field line concentration. So they assume that something with the magnetic field, that is the concentration of the magnetic field lines, that is the flux. The change in flux is producing this particular effect. The change in flux is producing a current. That is, the relative motion between the magnet and the solenoid is producing a change in magnetic flux. And by that, a current is being produced in the circuit. So that was the first assumption. So they thought for a while, and they were saying, okay, so relative motion between the magnet and the solenoid is producing this particular change. What else can produce this particular change? So again, in the next part, they consider a situation where there is a uniform magnetic field. So the field lines are going into the plane of the board because we can see the behind, the bottom part of an arrow. Remember, it is going into the field. So anyways, so this is a uniform magnetic field. And now what they did was, they put a solenoid loop or simply a current loop or simply a loop of let's say copper or something. It will be more easier. So they put a loop like this. So it's very simple. They had a loop like a bangle or something which is made up of a conducting material. That particular loop, they placed it in a uniform magnetic field. and they had equipments to measure the change in current. So right now the current value, or if I connect this to a galvanometer, the deflection is 0. So this was the second experiment they were doing. So if I connect this to a galvanometer, right now there is no change being observed. There is no change in the galvanometer reading, which means there is no current being produced. So we do know that relative motion between the magnet and the solenoid would produce a current. Now they are investigating, okay, is it because of the flux itself? Like, is it any other possibility? Is there any other possibility? And what are the factors that are influencing? For that, they constructed this particular situation and they are doing this. So initially they considered a magnetic field, uniform magnetic field, and they placed a loop made up of conducting material in that particular magnetic field. And what they did was, they tried to change the area. That is, this was here like this, and then suddenly, using some methods, they tried to stretch the particular current loop into a bigger size. That is, they increased the particular area of this particular loop. They tried to increase the area. So at first it was like this, and then immediately they tried to increase the area. There was a change in area. But then also they observed that there was a change in the galvanometer needle. That is, it deflected. Not just the relative motion between the magnet and the solenoid, but the relative change in size. That is, the relative change in the area is also producing an electric current. Or simply, when we change the area in this particular case, and a current was produced. So, is it true when we decrease the area also? They tried that also. They reduced the area also. They tried to reduce the area. Then again, the same effect was produced. Whenever a change in area was also produced, resulting an electric current was produced. That is, whenever we try to change the area of that particular loop, a current was being produced. That was the second result. Now, they also tried one more thing. What if I simply rotated it? That is, I keep this particular loop like this. That is, I keep this particular loop like this in a uniform magnetic field, and I try to rotate it. To either side, it does not matter. To that side or this side, it does not matter. So they try to rotate that particular loop. Now, is there any change? Actually, there was. Even though no current was flowing through this particular loop, when they rotated the loop in a uniform magnetic field, there was a deflection in the galvanometer needle again. That is, when they rotated it also, there was a change. There was a current being produced. Okay, now they were thinking that, okay, this might be due to some other phenomena. It is just working between a solenoid or a loop of conducting material and the magnet itself. There is no other way this can happen. But then they thought, okay, a current carrying solenoid will actually behave like a bar magnet. So can that cause any difference? So that was the setup behind the third experiment. That is, I'll just keep this here because we need this. So I'll just keep it there. So the third experiment was, they considered a current carrying solenoid. Let's say this is a current carrying solenoid, and this again was a normal solenoid connected to a galvanometer. So in the first experiment, it was just the magnet being put forth and backwards, but now it is a current carrying solenoid. But surprisingly, when I moved this current carrying solenoid also near this particular solenoid, which is connected to a galvanometer, no power source, there was a deflection in the galvanometer needle. So they just confirmed that it was due to the change in magnetic flux, or the magnetic field lines are inducing a change that is causing an electric current to be produced. Again, the relative motion of this current carrying solenoid, which is behaving like a bar magnet, is now producing an electric current in the coil that is having no connection to any power. A current is being produced, or a current is being induced. Okay, that is where the word induction comes from. No contact is there, and still a change in this particular field is inducing a current in the other one. A change in the field is inducing a current. So they were wondering why this happened. And after these experiments, they concluded three things. A change, that is a change in the field concentration, is producing this induced electric current, is producing an induced current. Now, with the second and third experiment, they actually found out that they arrived at an inference on how this current was actually induced or how this current was actually produced. And their findings were that, what were the findings? We also just saw, right? We also just saw what really happened. So when we try to change the area, that is when we try to increase the size or decrease the size, when there was a change in the area, there was electric current being induced. When there was a change in concentration of field lines also, there was electric current being produced. That is when the strength of the magnetic field decreased or increased. When I move the solenoid near or away from the bar magnet, the strength of the magnetic field is decreasing and increasing, because with increase in distance, the magnetic field strength decreases. So with increase and decrease in magnetic field strength, the current was being produced. And finally, I rotated this coil also, which means something there is also changing, and that something is the angle theta. How? Because field lines are going inwards like this. Field lines are going inwards like this. And whenever I try to rotate this coil, the area vector, I told you, for everything we are doing, there is a reason. And here, why we rotated the coil was that it changes the angle between the area vector and the magnetic field lines. That is, if this is the area, let's say this is the area A, there is a unit vector perpendicular to this particular area, which was discussed during most of the derivations we did, because that is how we measure the angle. That is, if field lines are passing through like this, coming out like this, then we use the area vector or the unit vector as a representation to measure how far it is from that particular vector to measure the angle. So when this coil is actually spinning, it is changing the angle between the field lines and the area vector. So when it is like this, it is at a particular angle, let's say 0 degrees, and when they are parallel to each other, when it is spinning, the area vector is changing, or simply the angle between the field line and the area vector is changing. Maybe it's 1 degree, 2 degree, 5 degrees, 10 degrees, 90 degrees, 180 degrees, like that it is changing. So the angle theta is also changing here. So strength of the magnetic field is changing, theta is changing, area is changing. All these changes is producing an induced current in the circuit. So this was the inference. So first they assumed and they figured out that a change in the electric field concentration, or simply a change in flux phi, this is magnetic flux, that is why it is phi B. So a change in magnetic flux is inducing a current. And why was that change produced? Either it was the change in magnetic field, or it was the change in angle theta, that is the unit area vector or the area vector and the field lines, and a change in area was also producing these changes. That is, it was inducing a current. This was the inference arrived by these three experiments. So this experiment is actually very important. They are going to ask you what is the inference, or summarize the experiments done by Henry and Faraday. So they considered three cases and they found out how this relative change in the magnetic flux is inducing a current. With three cases, they arrived at the conclusion that a change in magnetic flux phi B is producing an induced current, and that particular induced current is produced by the change in flux, or simply more accurately, a change in magnetic field, a change in angle theta, or a change in area is producing this particular effect. That is, it is inducing a current. So that was Henry and Faraday's experiment. but we are not done yet. We need to know what is magnetic flux. So in the electrostatics chapter, we already learned that what was flux. Flux was simply the measure of field lines passing through a particular given area. That is the definition of flux. And here it is magnetic flux, which means that if there is a magnet somewhere nearby, then the amount of field lines penetrating through a given area will be the magnetic flux. So we do know that flux is indicated by the letter phi. So this is phi, and since it is magnetic field, I am going to write phi b. If it is electric field, I am going to write phi e. So it is simply magnetic field, so phi b is equal to, if you remember the derivation or how we found out the electric flux, it is very similar. I told you both are symmetrical, so it is just the mirror image here also. It was E dot A in the electric field, and here it is going to be B dot A. So very similarly, B dot A. Since the mathematics is fairly similar, it is almost symmetrical. So I don't have to do it again just to prove that this is how the equation is going to come out, because we already proved it once. Instead of B, it was E. That is the only difference. But the flux lines will be indicated as such. Mathematically, it is vector B dot A, or simply we can write it as phi is equal to d A cos theta, where theta is the angle between the area vector and the magnetic field. That is, if we consider an area like this, if you are going to consider an area like this, there is going to be an area vector like this, and if there is magnetic field lines penetrating to that particular area, we are going to measure at what is the angle between these two. That particular angle is the theta angle. So if flux lines are passing through as such, then what we are measuring is with the perpendicular unit vector, or simply the perpendicular area vector, what is the angle that is made by the field line. So that particular angle is theta. So this theta is the angle between the field lines and the area vector. So we can just say that BA cos theta, or phi b, or simply the magnetic flux, is given by the equation phi b is equal to BA cos theta. Now we are going to find Henry's and Faraday's experiment much more clearer. That is, they found initially that a change in magnetic flux, that is, whenever the coil was brought near or far away, the amount of magnetic field line concentration was changing, or simply the flux density was changing, or simply the flux was changing. When there was a change in flux like this, it was inducing a current, or simply the change was more accurately measured. A change in magnetic field strength, that is, if B was changing, there is a change in flux. If A was changing, that is, the area was changing, there was a change in magnetic flux. And if there was a change in theta also, there was change in magnetic flux. All these contributed to the induced current. That is, a current was introduced or induced in the circuit when a change in any of these quantities were proposed or introduced. We can just say that the change in magnetic flux was producing that induced current, and the flux is given by the equation BA cos theta. So again, when we increase the area, there was a change in magnetic flux, that is, area was changing, there was a change in magnetic flux inducing a current. When the angle was changing, that is, when we rotated it, there was a change in magnetic flux, hence current was produced. When there is a change in magnetic field strength, when we moved it away or close to that particular magnetic field, a change in magnetic field strength produced a change in magnetic flux, introducing or inducing a current in the circuit. So based on these assumptions, or based on these contributions, Faraday and Henry arrived at their inferences, which later came to be known as Faraday's laws. So there are two main laws. We already saw them. It is just the conclusions of that particular experiment. So based on the experiment, Faraday had two laws. That is, the first law was whenever there is a change in magnetic flux linked with the coil or linked with the circuit, there was an EMF being induced. EMF just means it is voltage, or simply a potential difference was introduced or induced in the coil. That is, to make it more clear, the thing is that if you are using a loop, imagine that this entire board is a uniform magnetic field. If I am using a loop like this, then there is a current introduced whenever I try to spin it, whenever I try to move it. When there is relative motion, an EMF is induced or a current is introduced only when it is a closed loop. So that current can flow like this, or in the other way. Whenever there is a relative motion, whenever the current can flow inside a closed circuit, there is current being produced. That is when I am taking a loop like this, a closed structure. What if I am not taking a loop? What if I am just taking an element like this, just a line element like this? This is a conductor which is linear in nature. There is no closed ends, which means current cannot actually flow like that. So whenever there is an element like this, there is no closed structure for the current to flow. That does not mean that nothing is induced here. There is something induced here. So the more appropriate term should be an EMF. That is, a voltage difference or simply potential difference will be introduced here. A voltage will be induced. And that particular induced voltage is known as EMF, because we learned that we are going to call voltage from now on EMF, or simply electromotive force. So a potential difference will be introduced at these both ends when it is changing. When we are trying to spin this or when we are trying to move it closer or away, an EMF will be induced. So instead of saying current each time, that is, instead of saying a current is induced, we are going to say that an EMF is induced. If it is a closed structure, yes, current is induced. If it is a line element like this, current may be induced, current may not be induced. So we can accurately say that an EMF is induced. There will be a change in potential, which means current is obviously there because there is a change in potential. Current flows because there is a change in potential. Higher concentration to lower concentration, or lower concentration to higher concentration. There should be a change for the flow to happen. So it is more accurate that we say an EMF is produced. So the first assumption was, whenever there is a change in magnetic flux linked with the coil, an EMF is induced. There is no actual contact, there is no power supply, it is induced. It is induced in the particular coil, and an EMF is induced. That is one important thing. And the second law states that the magnitude of induced EMF, that is the value of EMF that is being produced, is actually equal to the rate of change of magnetic flux. That is rate of change of magnetic flux. We studied about rate of change. That is, along with time, some quantity is changing. So, for example, you studied about velocity, rate of change of displacement. That is dx by dt. Here it is rate of change of magnetic flux, which means d phi by dt. So the second law can actually be mathematically represented as, that is, the induced EMF E will be equal to rate of change of magnetic flux. So rate of change of magnetic flux will induce an EMF. That is the second law. And since the EMF is produced, is actually the direction of the current will be in such a manner that it opposes the relative change in motion. Why that is happening, we'll learn very soon. So just know that the current being produced will actually be in an opposite direction. So we can just say that it will be a negative sign here. The rate of change of flux will produce an EMF, and that will be, this negative sign is just there to indicate the direction. It is backwards. So just know this is how the equation for the second law actually mathematically mean. So this is for a single loop, and since we are already done the experiment with a solenoid, we can also say that, we can also write this as EMF E is equal to minus N d phi by dt. That is, N is the number of turns. That is, N is the number of turns. Because we did the experiment with just one loop, and that is this one. And we also did the experiment with a solenoid with n number of turns. So for that, the EMF will be in this particular form. So the only difference is the n will be added. The negative sign is introducing or indicating that the induced EMF or the current induced will be in an opposite direction. Why that happens, we will study very soon, but these are the mathematical equations for the Faraday's laws, so, especially the second law. Always remember, it is induced EMF and it is caused by rate of change of magnetic flux. Now I told you that a current is being introduced into the particular circuit. That is, if I produce a change, if this is a loop, that is a conducting loop, and I bring a magnet like this, let's say this is a magnet, and if I bring this magnet closer or out of this particular loop, there is a current being introduced or current is induced, and EMF is actually induced in that particular coil. But I did not tell anything about the induced current. That is, current is induced, but I don't know if it is in that direction, is it in this direction, or is it like current is the all powerful quantity, it can go in any direction it wants. No, there is actually a rule and there is actually a phenomenon behind that particular current being induced. That is, this particular current that is produced in the coil is in such a manner that it opposes the relative motion. That is, when I try to bring this magnet close to that particular loop, what happens is that current flows in such a manner that it tries to reduce or it tries to repel away this relative motion. How can current do that? Current is not like any action hero or like Mahesh Babu who just says, just go out like this. He can't just do that, right? So what happens actually is that when we already know something, whenever a current is flowing through a conducting material, magnetic field lines are produced in it. If it is a straight line, in circular manner. If it is a closed loop, then we know magnetic field lines will be produced like this because we read the previous chapters. So whenever there is a relative motion like this and current is being introduced here, it is also inducing a magnetic field there. So this particular magnetic field induced here will oppose this particular relative motion, or it is trying to tell this particular magnet, don't come in, don't come in, don't come in. Please go away, please go away. But when this magnet tries to enter, it is constantly changing that magnetic field, meaning more current is being introduced. Meaning it develops magnetic field saying don't come in, don't come in, don't come in. So the process or the thing you have to remember is that whenever we are trying to push this magnet near this particular loop, a current is being introduced, and the current flow just so happens to be that it is in a manner that it opposes the relative motion. That is, we do know that when current is flowing through this particular conducting material, using the right hand rule, we can determine what direction is the magnetic field in. Just like that, for a current carrying loop, there will be north and south poles being produced. So depending on the relative motion of this particular magnet, if north pole is entering or south pole is entering, depending on that, current will flow in such a manner that it opposes that particular pole. If north pole is coming in, the current will flow in such a manner that this particular area will develop a north pole. Same like poles will develop here. So, and if south pole is trying to enter here, it will develop south pole. So, it will always try to repel or obstruct that particular motion. Imagine like it's friction. Like when we are trying to walk, the ground will provide friction. The air will provide air resistance so that it is opposing our relative motion. Just like that, when the magnet is trying to enter, it also opposes that particular relative motion. And when we are inside that particular loop and we are trying to take it out, this current reverses because the magnetic flux is now changing. Now, when we are trying to go in, it says don't come in, don't come in. When we are in, keeping there for a while, and then we are coming out like this, then the magnetic field or this particular loop is saying don't go, don't go, don't go. Because when we are trying to take it out, the current will flow in such a manner that it will oppose that particular relative motion. It will hold that particular magnet in that particular place. So the current flow when the north pole is entering will be in a particular direction, and when we are taking out the magnet, it will be in a particular direction to oppose that particular motion. And this particular rule is known as Lenz's law. So what Lenz's law actually states is that whenever there is an induced EMF produced by that relative motion or any change in the flux, that is, the polarity of the induced EMF is in such a manner that it tends to produce a current which opposes the change in magnetic flux. So when we are introducing that particular motion, that is when the solenoid is there and when we are trying to move the magnet into the solenoid, what happens? There is a change in magnetic flux which is inducing that current. So this particular current being induced or this particular EMF being induced will be in such a manner that it will oppose the change in magnetic flux. It will try to reduce that particular change. Every system wants to be in a state of rest, doesn't want change. So the change will be in such a manner that it tries to oppose that particular change in magnetic field. That is Lenz's law. So if there is a coil and magnet is going into that particular coil, then the current will be produced in such a manner that it opposes that particular pole coming in. And when we are inside the solenoid and we are trying to take out the magnet, the current will be flowing in such a manner that it opposes that relative change. The current will be producing a magnetic field that is attracting the magnet inwards. An application of Lenz's law, or a more clear indication, is that when the north pole is coming into the pole, it wants to relatively oppose that particular motion. It relatively wants to say, brother, stay out. So it wants to say that don't come closer to me, which means it produces a current in such a manner that it produces like poles here, that is north pole here, and that current motion should be in the anti-clockwise direction. If the current is in the anti-clockwise direction, here the loop will develop a north polarity. So the way you can remember it, that you can draw it like this. You can draw an N like this. The ending of the N will indicate an arrow, that is anti-clockwise direction. Similarly, when we are trying to pull back the magnet, after it is being inserted, then this particular loop will develop a current such that it tries to oppose that particular relative motion, which means it will try to attract the magnet in. Stay in, don't go out, just like that. So that particular current flow will be in such a manner that it develops south pole, which means right opposite to this. The current flow will be in the clockwise direction, or simply you draw an S. So it is clockwise direction. So if you have trouble remembering it, you can use either one of these two methods, or simply remember it by anti is from north. That is, anti is from north. Anti-clockwise will produce north pole, and similarly clockwise will produce south pole. So only thing you have to remember is anti is from north. Anti is coming from the north side of India, so anti is from north. Is anti-clockwise will produce a north pole, and south pole will be produced by clockwise direction of the movement of current in that particular loop. So those are two things you have to remember about Lenz's law. So Lenz's law just states that whenever there is a change in magnetic flux, the induced EMF or the induced current will be in such a manner that it will try to oppose that particular change. So I hope you have understood everything about induced EMF, how Faraday and Henry conducted their experiments, and the change in magnetic flux will induce an EMF. So in the coming classes, we'll discuss more about Lenz's law and their applications. So until then, I'll see you on very soon. Thank you.